Since not all games have strictly or weakly dominant strategies, we want to also consider some other equilibrium or solving methods for these simple, simultaneous, non-cooperative games. So consider another just simple 2x2 game where you have two players and each has two strategy choices. So you've got two players and each player can choose to watch Harry Potter or Avengers. Player 1 slightly prefers Harry Potter to Avengers. Player 2 prefers Avengers to Harry Potter. And both players prefer to watch a movie together rather than to watch a movie alone. So we'll just look at this in matrix format. Again, the payoffs are relatively arbitrary, but just set up to represent these preferences. So player 1 can choose Harry Potter or Avengers. Player 2 can choose Harry Potter or Avengers. If they both choose Harry Potter, that was player 1's preference, so they're slightly happier. If they both choose Avengers, that was player 2's preference, so player 2 is slightly happier. And then they can each watch movies alone, which is a lower payoff. Okay, so here, player 1 chooses Avengers, player 2 Harry Potter. Here's where player 1 chose Harry Potter and player 2 Avengers. So what we're going to describe now is what we call a Nash equilibrium method. And a Nash equilibrium relies on what we call best responses. So a best response is conditional on possibilities of your opponent's choice. What is the best play? All right, so let's see. Let's look at player 1 choosing Harry Potter or Avengers. So if player 2 has chosen Harry Potter, what is the best response? Player 1 would get 3 for Harry Potter or 1 for Avengers. So the best response to HP, Harry Potter, is to choose Harry Potter. So if player 1 believes player 2 has chosen Harry Potter, the best response is Harry Potter. Right? What about if player 1 believes that player 2 has chosen Avengers? Player 1 would then get 1 for Harry Potter or 2 for Avengers. So the best response here is Avengers. And what we can see is that there is not a strictly or weakly dominant or dominated strategy in this game. Remember, a strictly or weakly dominant strategy was better no matter what the other person was picking, and here we don't have a strategy that's best no matter what. All right, quickly, what about for player 2? If player 1 chose Harry Potter, better off with Harry Potter. If player 1 chose Avengers, better off with Avengers. So once again, not a strictly or weakly dominated strategy. So we'll talk about this Nash equilibrium, and a Nash equilibrium occurs when each player is playing a best response to the best response of the opponent, or in other words, no player has an incentive to deviate. So I've used some colors here to illustrate the best responses for each player. A Nash equilibrium will exist when we have an overlap of these best responses. So conditional on, let's make player 1's choices red. Conditional on player 2 choosing Harry Potter. Player 1 is better off choosing Harry Potter, so we've highlighted that in red. Conditional on player 2 choosing Avengers. Player 1 would be better off choosing Avengers, so we've highlighted that 2 in red. 2 is better than 1. All right, let's put player 2's best responses in blue here. So conditional on player 1 choosing Harry Potter, player 2 would get 2 for Harry Potter or 1 for Avengers, should choose Harry Potter. Conditional on player 1's choice of Avengers, player 2 would get 1 for Harry Potter or 3 for Avengers, chooses Avengers. Right, so in this game, we actually have two pure strategy Nash equilibria, which are each chooses Harry Potter and each chooses Avengers. And the Nash method isn't able to make a prediction about which of the two equilibria will occur. It is true, however, that if a strictly dominant strategy equilibrium exists, or if a dominant strategy equilibrium exists, it's unique, and it's also the Nash equilibrium. So just quickly, let's go up here to one of these, right? So what would be the Nash equilibrium? So the best response for player one to silent is right here. Let's just make that blue. The best response to betray would be betray. So let's make that blue. Or did we do red for player one? Yeah, we did. All right, let's make them red so we're consistent. All right, so the best response for player one to silent would be betray. The best response for player one to betray would be betray. That's a dominant strategy. What about for player two? If player one is staying silent, that would be -1 for silent or 0 for betray. So let's make this one blue now. And then best response to betray would be -5 for silent or -4 for betray. So betray. All right, so here we have a Nash equilibrium, which is betray, betray, and it coincides with our strict dominant strategy equilibrium. Right, but here, because we do not have dominant strategies, our dominant strategy would not be able to rule out any of these, and our Nash equilibrium basically rules out these two right here. So we've got what we call a coordination game. All right, two pure strategy Nash equilibrium. What about another game with multiple pure strategy Nash equilibrium? We call this one the game of chicken. Each player can stay on course or swerve. Let's do red for player one's best responses. Suppose that player two is going to stay on course. Player one would get -10 if they stay on course and collide, or -1 for swerving and being the chicken. If player two is going to swerve, player one would be better off staying on course. 10 better than 0. All right, blue for player two. If player one is staying on course, better off swerving. If player one is swerving, player two is better off staying on course. 10 more than 0. So we have two pure strategy Nash equilibria: swerve, stay, and stay, swerve. All right, we can also apply this concept to larger games, and best responses can also be ties. So player one's best responses, I've already got them highlighted here. So if player two is choosing A, player one would get -1 for A, 3 for B, 0 for C, best response B. If player two chooses B, we see that we have a tie. Player one should choose either B or C, so we've highlighted them both. Player two chooses C, once again, player one has a tie. A or C will yield a payoff of 2, so either one is a best response. What about for player two? If player one is choosing A, they can have -1, 0, or -2. B is the best response. If B, you can have -3, -1, or -1. So B or C would be a best response. If C, 0, -1, -2, A is the best response. All right, so we're looking at an overlap, looking for an overlap of best responses, which occurs right here at BB. And once again, neither player has an incentive to deviate. If player one is choosing B, player two is going to do worse off, -3 or the same, by deviating. And player one is going to do worse off or the same by deviating, so neither has an incentive to change from BB. We also want to briefly introduce mixed strategy solutions, and I'm actually not going to go through here or test on mixed strategy calculations, but I did put an example of how to do it. In a mixed strategy, each player assumes that there is a probability distribution over the opponent's moves. So player one assumes that rather than picking one of these movies for sure, player two will watch Harry Potter with probability X and Avengers with the complement probability. So it always has to add up to 1. It's easier for us to just use 1 minus X. This is saying if player 2 is choosing Harry Potter with, say, a 75% chance, then the chance of Avengers is the remaining 25%. All right, in this case, we would use an expected value calculation. So just kind of briefly, for those who are interested, suppose player 2 is picking Harry Potter with probability X and Avengers with probability 1 minus X. What's the value of each of player 1's strategies? Well, if player 1 chooses Harry Potter, with probability X, player 2 also chose that, and player 1 would get a payout of 3. So the value is 3 times X plus, also with a probability 1 minus X, player 2 chose Avengers, in which case player 1 would get 1. All right, so this is what we're seeing here. The expected value of Avengers would be, with probability X, player 2 chose Harry Potter, gets a payout of 1. Probability 1 minus X, we get a payout of 2. Right, and then ultimately a mixed strategy solution is going to exist when a player is indifferent between the pure strategies. Again, just because we don't have a ton of time left in the course, I'm not going to go too deep into mixed strategy solutions, but basically I just want you to know that they exist. We won't spend much time on calculation. Right, so one game where mixed strategies is useful, and again, we're not going to actually test on the calculation of this, but it's a good exercise for yourself to verify that here in this penalty kick game, the kicker can kick left, center, or right, the goalkeeper can go left, center, or right, and the kicker scores if the goalkeeper chooses the wrong direction. So you should go ahead and verify that there is no pure strategy Nash equilibrium of this game, no overlap of best responses. So the only equilibrium of this game is going to be in mixed strategies, and we could solve for a mixed strategy distribution, although we won't.